Okay, the purpose of this screencast is to introduce you to slightly more advanced features in PRISM, and especially some of the nuts and bolts involved in doing curve fitting analysis. So I will start up PRISM. And while that's going on, I will note that what we're going to do is we're going to simulate some data. We're going to add noise to it. The previous screencast did something like this. In the current case, we're going to simulate a non-cooperative binding isotherm. So an independent site binding isotherm as a function of total ligand. So I'm going to simulate data for such an experiment. I'm then going to add noise to it. We're then going to do the curve fitting, and by the time that's done, you will have seen all the steps involved in setting up, in simulating data. We'll go through that one more time. In setting up a curve fitting analysis using an equation that you write yourself, configuring all the software widgets that need to be done to do that. And then once we've done all that, we will then take a step back and look at sort of the scientific and conceptual content here. And what you will see is that the parameters that you get once you add noise to the data, the parameters that you get from the curve fitting analysis, what the curve fitting analysis gives you is the most probable estimates of the parameters given some error model. You'll see that once you introduce a significant amount of noise into the experiment, the most probable estimates of the underlying parameters describing the experiment start to move away from the actual values. So this exercise is informative because in this case, because we're simulating data, we know exactly what the parameters should be, and then we'll know when the estimates from curve fitting do not exactly match them. So this is really quite a important. The main purpose of the screencast again is to teach you a little bit more about using PRISM, but there's a moral to this story that is quite important, which is understanding the limitations in experimental data in terms of your ability to infer the underlying parameters, and the fact that noise has a strong influence on the quantitative accuracy of the parameters inferred from experiments. So let's get started. I'm going to kill this. I will close this old notebook, and we'll make another PRISM. We'll make a new. Sorry, I closed the old project. I'm going to make a new project specifically for this exercise, and I will start with an empty data table. Because we're going to simulate data that'll create its own data table effectively. Oh, it does. I'm sorry, table only, no graph. Okay, this will come up in a moment. Oh, I'm sorry, we still have to choose the format of the data. Sorry about that. We're not really going to use this one anyway, so we'll pick whatever. There we go. And now the first thing we're going to do is new. No, I'm sorry, the first thing we're going to do is do an analysis. We're going to hit the Analyze button, and we're going to now choose Simulate and Generate, Simulate Data with Random Scatter. So we've done this, the first screencast on PRISM covered this in the context of a linear regression. We're now going to go one step further and enter our own binding model for the simulation. For the exercises for the course, you're going to be, I don't think we're going to actually ask you to write your own equation for curve fitting. My intention is that you will be given the electronic version of the equation, PRISM ready, and so you should not have to do some of the steps we're about to go through yourselves. But going through them will let you understand a little bit more deeply how PRISM is operating. And then also, in the process of doing this, we will have to configure things called initial values. The initial values are quite important, and so we will go through that when we set up. Every time you set up a new equation, you have to make default assumptions for initial values. You can then modify those assumptions when you do an actual curve fitting exercise. So this material, in addition to the entry of the equation, goes beyond the nuts and bolts of PRISM that were introduced in the previous screencast. So I think to start with, let's start with the equation. So go to equation. the plus sign enables me to create a new equation. So typically if I'm doing this, I will start with an existing equation and edit it, so I'm sure I got the syntax right. But today I'm going to do it cold. Hopefully I won't make any mistakes. And so I'm going to call this a quadratic binding isotherm y bar versus LT for total ligand. Okay, and I think that should be good enough for now. I think that's a good name for the equation. Now, well, actually, maybe put this is for W4082. In your own version, you probably don't need such an elaborate title because I have tons of equations. I'm going to put a little bit more in so I know where this one came from as I see it among the sea of equations in my version of PRISM. So 2016. Okay, and so what I'm going to do is actually enter the formula for the quadratic binding equation. I'm going to do it from scratch. So I am going to first describe something D, which stands for discriminant. This is one term from the quadratic equation. The square root term in the quadratic equation is typically called the discriminant. When you're setting up the mathematical formula that describes a non-cooperative binding as a function of total ligand, involves solving a quadratic equation. So D represents the discriminant from that solution of the quadratic equation. So having done this many times, I actually know by heart that the discriminant is KD plus SRT. So KD is dissociation constant, SRT total receptor concentration plus LT total ligand concentration. Now, so a noteworthy point here is that I've just made these variables up. I have not first defined them, I've just made them up. I guess one important point to know is that special variables in PRISM are x and y. The dependent variable that will be graphed is always x, or the one that will be simulated. The independent variable in any graph or simulation is called x. If you use x, it will assume that's the independent variable. Y is the dependent variable. So x and y are the horizontal and vertical axes on the graph, or the abscissa in the ordinate, to use more formal mathematical terms. Right. So the quadratic equation describing a non-cooperative binding has a discriminant of KD plus SRT. I'm not going to put the concentration brackets here because that gets to be tedious, and actually PRISM will interpret them differently. So PRISM interprets equations in a pretty sort of intuitive, what you see is what you get kind of way. Its syntax is similar to most widely used programming languages. There are some differences. If you've done any programming, this is going to probably look very easy to you. If not, it still is going to look, more or less like the sort of obvious algebraic interpretation of whatever you write. And so equals, of course, is equals, plus is plus. Parentheses separate, group together operations that should be performed first. And then anything that isn't a standard variable, x, y, or an operator, PRISM will automatically assume is a parameter. So PRISM will automatically create a parameter KD, a parameter SRT, and a parameter LT. Okay, so good, so much for that. Now I know that the solution to the quadratic equation in this place, so I'm going to say now I know that when you solve the quadratic equation, the formula that you derive is that SRL, the concentration of the binary complex, is equal to 1/2 or 0.5 times negative, let's come back to this, negative B. And then the quadratic equation would be plus or minus, but the root that actually solves the physical problem is the minus. It's negative B minus D. And immediately I've made a mistake here. So actually B is equal to KD plus SRT over plus LT. Sorry about that. The discriminant is actually equal to, you will have heard this before, square root. In most programming languages, that's the symbol for that is, the string representing that is sqrt. It's the square root of b squared. In most programming languages, to raise a variable to an exponent, you do use this character. So it's b squared minus 4 well, the quadratic formula is the discriminant is b squared minus 4ac. In this case, again, I know the quadratic equation underlying this by heart. It's srt times lt. And we actually need the multiplying symbol there. Okay, and this is almost all we need. And I think the only final thing is I'd like to plot this as fractional saturation. Well, what is fractional saturation? So it's SRL, the concentration of the binary complex divided by SRT is the fractional saturation of the receptor. So this shows one of the powerful capabilities of PRISM, which is that I can put in sub-equations, and PRISM will know how to combine these internally. And so that means I can avoid writing very, very complicated equations with lots of variables all strung together. Now, in the equations we're going to give you to actually solve problems, I think most of them are set up as sort of a single equation with lots of variables. There are some advantages to doing that for some applications. On the other hand, when you're not deeply familiar with something and you're not a master of PRISM foo, it is much easier to do it the way that I just showed you here. So I first said b is a variable because it's not one of the standard PRISM variables, which are basically x and y. It will assign this to be a new variable, and so this is it will interpret this as saying some new variable v equals a variable or parameter kd plus a variable or parameter srt plus a variable or parameter lt. So that defines a variable b. Now I can say that d, the discriminant, is the square root of that variable b squared, so it will use this equation as long as it occurs before it in the as you go down the entry box. B squared minus 4 times SRT times LT, and then I will say, and so now I will write an equation, the solution to the quadratic equation. SRL, I have defined a new variable. That variable is supposed to represent the concentration of the binary complex. So SRL equals 0.5 negative B minus D. And so basically I have taken a rather complicated quadratic formula that would have tons of terms, and I've broken it down into simple subterms. And I'm basically letting PRISM do the algebra. And then my final, I'm saying what I want to plot in the end is y is what PRISM will always plot, and I'm saying I want that to be the complex of the binary complex divided by SRT. So there is one problem here. I started out writing LT because that's supposed to be total ligand. That sort of can give you a clue as to, well, it lets you understand what it is I'm inputting. But in this case, we actually want to plot and analyze data as a function of total ligand. And so total ligand is going to be on the x-axis or the abscissa. And again, in PRISM, the variable on the x-axis has to be x. So we have to, in this case, LT is conceptually, a useful mnemonic to us, but PRISM, if we want this on the x-axis, PRISM needs it to be x. So B is KD plus SRT plus x, that is representing LT. D is B squared minus 4 SRT LT, right? So that is, once again, x. SRL is 0.5 times negative B minus D, and the fractional saturation is SRL over SRT. And so basically there are two parameters in this. So we have a dependent variable x, which is LT. We have no other occurrences of LT. That's good. We have to replace them all by x. We have the dependent variable, which is fractional saturation. And in the middle, we've defined on the fly, variables that are useful to set up the math. We define this term B. We define D. We defined the complex concentration as SR. We named that SRL. We said mathematically it's 0.5 negative B minus D. And then we can define the dependent variable y bar in this case, but I can't call it y bar because PRISM insists that the y-axis, the variable you want plotted on the y-axis is called exactly y. The variable you want plotted on the x-axis is exactly x. So we say the y variable on the y-axis is SRL, the binary complex concentration, divided SRT. That represents what we've been calling y bar. Okay, and I could put in a tip or a description, but I think the description up here is sufficient. Well, maybe tip, well, description, let's say KD, dissociation constant, SRT, total actual receptor concentration. Those are really our only two parameters. Quadratic binding isotherm. That implies it's applicable only to a non-cooperative. Why don't we make a note of that? Equation applicable to non-cooperative independent site. These are synonyms. Independent site binding reaction. And actually to a binary, meaning the two components involved in it. Okay, so we're all done here. Now we need to go for the initial values. So we have two parameters here that we've sort of defined the names of on the fly and that PRISM will use. So when we come over here, we should see two initial values. So KD, the initial value to be fit. So in some cases, when you run a binding experiment, well, as we've talked about in class, the free ligand concentration at 50% saturation, which is y bar equals 0.5, the free ligand concentration will always be equal to KD. The total ligand concentration can be quite different. But under some experiment, with some kinds of experimental design, the total ligand is similar to the free ligand. So if you have to pick a guess as to the dissociation constant, a reasonable guess is the ligand, the total ligand concentration. Again, this isn't necessarily going to be true, but we need to make a guess as to what KD is. If we pick the total ligand concentration at 50% saturation, that's in the case where total ligand and free ligand are about equal, that will be a very good guess. In other cases, it will be a reasonable starting point for optimizing the variables. And so how could we do that? So the value of x at y mid is one of the options PRISM gives you. And so what this says is it's going to use as the initial estimate of KD the value of x at y mid, the midpoint of the y data. So what it will do is look at all the y values, find the one in the middle between the top and the bottom, and it will use that as its initial. 1 times that value will be the initial estimate of KD. In the case of good data, where free ligand is about equal to total ligand, this is discussed extensively in the lectures, that's going to be probably a very good estimate of KD. In other cases where free ligand is very different from total ligand, it could be far off, but it's still a reasonable starting point. And what we need to get the curve fitting running is a reasonable starting point. So that's good. Now SRT, this on the other hand, is something that is not readily, does not have, under any circumstance, a necessary relationship to the data. This depends on how much receptor we put in the experiment. You could put almost anything here. We'll have a chance to change it on. I think we could just say for the moment that we're using 1 as our default value. We'll have a chance to change the default later on. So now default constraints, I'll talk about that just in passing. No constraint means that it will let KD be whatever you want it to be wherever it goes. In some cases, the curve fitting becomes unstable, and so in those cases, it can be useful to constrain it. That's an advanced topic you don't need to worry about now. So we could constrain it, for instance, to be greater than 0 if we wanted to make sure it never went too low. Don't worry about why you would do that now, but just note that it's possible. We can also say a shared value for all data sets, so that's quite useful. So what we could do there is have 5 binding experiments on the same receptor. We could now, in PRISM, have it fit simultaneously all 5 of those curves. In PRISM would then, basically use all 5 of them to estimate the KD. Another way of putting it would constrain the KD to be the same for all 5 of the analyses. But at the moment, we're not going to constrain these things. Transforms to report. I'll just briefly talk about this. I don't think you'll need to use this, but what this does is it allows you to calculate simple functions of the different parameters that you're fitting. Why would you do this? Well, if it's a simple function, and this will only do very simple functions. If it's a simple function, you really don't need the program to do it for you. You could do it in Excel or in a calculator. But if you do that, you will just get the most probable value. If you put the function into here, it will actually also give you the error bars or the uncertainty in the function. And this involves something called error propagation, which we'll talk about in Module 2 of W4082. Okay, but that's pretty much what we need to do to set this up. So we entered an equation, a new equation that we made up from scratch. Well, that I entered from scratch. This is the equation describing the fractional saturation of a receptor as a function of total ligand in a non-cooperative or independent site binding equilibrium. So that's good. We've defined just default rules for initial values, and in this case we say we don't want any constraints. Okay, good. We're done. So now we're back to where we started, in a sense, which is the data simulation menu. Now that we entered the equation, it will also be available for data analysis, and we're going to do that before too long. But to begin with, let's simulate some data. And so I'm going to say I want to simulate a binding experiment. Later on, this is a great thing to play with to see how it's a great experimental design tool. I can see how if I change the range of X values I explore, or spread them out more, or compress them together more, do I get more reliable parameter estimates once I introduce noise into the data? A big deal in binding experiments is whether you go to saturation or not, and what effect the lack of saturation has on your ability to estimate the underlying binding parameters. You can play with that here too by deciding how much data, what range of data you want to simulate. But in this case, I think what we'll do is we're going to go each value. We're going to say we're going to do an experiment, let's say with 21 values, where we start at 0 and we go 1 each time. So basically, this will go from 0 to 21. We're not specifying the units. They could, when you do the arithmetic, the units are relevant. When you interpret experiment, the units are very relevant. These could be micromolar or nanomolar, but anyway, if they were micromolar, the KD would then be defined. If we're using units that are micromolar, the KD that is estimated from curve fitting would be in micromolar. If we use nanomolar, the KD would be in nanomolar, and similarly, SRT would be in micromolar or nanomolar, depending on however we input the data. So that's slightly subtle. Don't worry about that if you don't catch that now. Okay, so the equation we're going to use for simulation is the one we just entered, quadratic binding isotherm y bar versus LT. Great. Parameter values. I'm just going to simulate one data set for today, but I could do several of them, and that can be quite useful. But today I'm just going to do one. And I'm going to then say, I'm going to simulate data with a KD of equal to 2.0. And KD equal to 2.0, and I'm going to say SRT, I'll put the brackets here, SRT also equal to, actually I'm going to make this a little bit bigger for today's exercise, 4.0. And so now this is just the title. It will enable me to see on the graph what I've done, but my title in this case are the values that I want to use for the simulation, so I'm going to put in 2.0, and I'm going to put in SRT 4.0. And now random error, talked about this in the previous screencast. Today we will put in Gaussian absolute error. The other one worth noticing here, this is pretty sophisticated. I think it's too much to tell you about a lot of what's going on here today. But Gaussian assumes that you have a normal distribution, or a Gaussian, the error follows a Gaussian function, with the peak at the Gaussian function being at the true value, and the spread in the Gaussian function being given by some standard deviation. In this case, because we're plotting fractional saturation, the binding isotherm that we simulate will go from 0 to 1. So, it's 10% error at the top would be a standard deviation of 0.1. And so, again, this curve is, the equation I entered is simulating fractional saturation data. And fractional saturation goes from 0 to 1. So 0.1 would be 1/10 of 1. So this would be 10% noise at the maximum value, And what we say when we're saying absolute, that means there's also an absolute 0.1 noise at all points. So data error models are sort of a field of study, or at least a field of requiring substantial thought, and I don't want to go into that now. The two most common would be absolute, and so this would say, suppose you're measuring something on some detector, say counting photons. Absolute would mean if the fluctuation in every measurement was plus or minus the standard deviation in every measurement, let's say, was plus or minus 20 photons. That would be absolute. If the fluctuation were proportional to the magnitude of the signal, so let's say with 100 photons, maybe the fluctuation would be plus, the standard deviation would be plus or minus 10. With 1,000, maybe it would be plus or minus 100. That is relative. That means it's the same fractional fluctuation at different data points. Why would that happen? Well, I'm not going to go into that now, but it does happen, and so it's worth noting that you can also have a relative Gaussian error. But today we're going to use an absolute error of 0.01, which is 10% of 1.0. So let's go ahead. We should be ready to simulate. Okay. And something now went grossly wrong. This doesn't look like a binding curve. Well, we do at least have data going in steps from 0 to 21. This was somewhat of a hazard of entering a binding curve on the fly. Anyway, I can actually now change this equation. So just to review what I just did, this is the change menu, change analysis parameters. One of the analysis parameters is the equation. I can actually change the equation. And yes, simple mistake, I think. The B value is actually negative KD plus SRT plus LTA, I believe. So anyway, this does show how you can change things very easily. I've now changed the equation. I will not change the initial values. I'm going to say OK to that. I'm not going to change my simulation parameters either. I'm going to see if this now looks like a proper binding isotherm, which it does. Yeah, sorry about that. But mistakes were made and now mistakes were fixed. Sorry about that. But I think that maybe is informative in some ways. So, all right, now, so I'm just going to make this bigger, just easier to see. No substantive value to this, but it makes it easier to see. I'm going to, again, I want everything to just be bigger here, just so I have a reminder what I'm doing. Well, here we go. So I'll set up LT micromolar. That's fine. This should be Y bar. Good. It's all set up. I've done this before. That's why it knows these titles. It knows these are titles that I like. And simulated data is fine. I might actually put in simulated data. KD equals 2, SRT equals 4, just as a reminder. Okay. So now what I can do is try to curve fit these data. And so now I've simulated data with some noise. And so we don't expect them to match the theoretical relationship exactly because the noise skews the measurement from the ideal value. Maybe make these measurements a little bit bigger. And maybe I'll make this the data points red. This can stand out more when I do the curve fitting. Voila. All right, now, so let's curve fit this and see what we get. And how do I do that? Well, now I go back to Analyze. Rather than picking Simulate and Generate, which is down here, I will pick Nonlinear Regression Curve Fit. I will now pick the equation I put in, right? We should get exactly the same result back in a perfect world, but a world with noise, which real experiments they always have some, and it's usually significant. We are not necessarily going to get back what we put in. That's sort of the scientific moral of this exercise. So now compare. This is too complicated to go into now. We generally don't use this. We generally do this is related to what model really fits your data best. We tend to do that ourselves offline. Anyway, that's too complicated to go to now. Constrain, I told you about that earlier. We could constrain KD, let's say, to be greater than 0. I don't think we'll need to do that. If we had multiple data sets, we could constrain KD to be a shared value between all the data sets. A very useful thing at some points is to make, you can constrain well, actually, you can constrain it to be a predetermined value. And I won't explain to you now why this is useful, but before long you'll probably see that there's some utility to this. In this case, it says data set constant equals column title. If on the data table page I put a number in the column title, it will then use that number and it will force the KD to be that number. For KD, that's not particularly useful. However, for SRT, there are times when it will be useful for us to do that. And you'll begin to get a hint about that as we go forward in this screencast, but I'm not going to go through it in depth today. So we're not going to constrain anything for now. Weights. This has to do with error model, and this is too complicated to go through and explain until you understand more about Gaussian statistics. Initial values. So we do need initial values. It's picked them automatically. It's picked as an initial estimate of KD 5.3. So we told it to pick the x value at the midpoint of the y range. So the y range goes from a little bit less than 0 up to about 1.05 or something. So the middle of that would be about 0.5, and it's going to pick the x value. It'll actually rank and it's going to pick the x. So it's picked basically this x value. Well, it's done some interpolation. Because we simulate, if you look what it did, we simulated data at integer values of LT. It picks 5.3. It's done some interpolation in here to find the midpoint. But basically, so it's saying the midpoint is about 5.3. That's about right. That's the midpoint of the Y range. Here it's saying the SRT is 1. That's, again, an arbitrary initial estimate, but it should be a good enough estimate to work. Range. The minimum, this is now defining what range it will plot the curve in for the moment. So when it will find the best, the parameters most probable, it will find the most probable parameters explaining the observed data according to the equation that you have selected. So we'll get into model and hypothesis testing in the next course module in W4082. Anyway, once it is calculated the most probable parameters, it can then plug them back into the equation and plot the resulting curve, which is what it will do and what we'll see in a moment. And so let's just let it do it automatically today. Output, it's just telling you things about the data table, and we're not going to worry about that today. Diagnostics, this is some pretty sophisticated stuff, but I think it is also beyond the scope of what we should work on today. So let's just go back to fit. And I guess one thing to notice here when you're fitting, actually they've moved this between since the last version of PRISM. Actually, so diagnostics, there's one diagnostic that is worth noting. Don't fit the curve. So actually, I'm going to do that first. I'm going to fit the curve with maximum number of iterations. As you will learn in detail, if you're in W4082, the curve fitting process is an iterative computational approximation process. You can limit the number of iterations. With the data that we're going to be working with this semester, you won't need to do that. You can also don't fit the curve. So what this will do is this will then just plot the equation using the initial values of the parameters. So let's just try that and see what happens. Okay, so we have a bind. So what this is useful for the following reasons. This tells us what kind of curve our initial parameters give us. Our initial parameters give us a curve that doesn't seem to be an exact match, but it is a close match. In curve fitting, you do want your initial parameter estimates to get you close to the right answer. If they are not, you can get caught in what's called a local minimum. So you want to start with parameter estimates that give you something that is at least a reasonable approximation to the data. It doesn't have to be exact. If it's really far off, you might get trapped and you might not get a good curve fit. Again, this stuff will be explained in some detail in Module 2 of W4082. We could be way further off than this and it would still likely converge. But anyway, this is sort of a nice sanity check, right? Because we can see that our initial parameter estimates are close to the data. And so now what we'll do is we're going to we'll actually fit the data, and we're going to see that the parameters move around. So let's go back to that. We're going to redo the nonlinear fit. I want to now fit the curve. I will just remind myself of the initial values. I started with a KD of 5 and an SRT of 1, so let's hold that in our minds for the moment. Let's go back to fit. Let's not worry about this. Just by default, it's least squares fit, which is what we want. It's the appropriate one for Gaussian statistics. And so let's go ahead and fit it. And so what you could see there very quickly is that the curve shifted up. And why did it shift up? Well, the curve fitting procedure determined that the, so I've now gone over to we were looking at the graph. I've now gone over to the results tab. I'm going to the nonlinear fit of simulated data page. This actually tells me the values that it's calculated. It has calculated that the most probable value, given our error model for the observed data, is KD of 1.8 and SRT of 4.98. And so our assumed initial values were KD of 5.3, so that's moved to the most probable value given our error model in our data. Our initial value here was 1, and it moved up to 5. And of course, because in this case we actually simulated the data, we know what the true answers are in the absence of the noise. The KD we put in was 2, so we're actually not so far off from that. And it's at some point in the lectures I will explain why this experimental design that I implemented is likely to give us a pretty good KD. And the SRT is 4.98. And so the true value from in our simulation was 2, and so this is about 10% off. The true value here was 4. This is about 20% off. It's now giving us estimates of the standard error, effectively the standard deviation, the anticipated uncertainty, well, the estimated uncertainty in the parameters. It's saying the KD is 1.8 plus or minus 0.68, so the true value is certainly within that range. But note, the KD, we don't know the KD very well. It's going to give us also the 95% confidence limits for the KD. It's saying the KD is between 0.3858 and 0.3858 and 3.24. So the 95% confidence limits on the KD vary over a 10-fold range. So we do not know the KD that well when we have that much noise in a data set acquired in that manner. So I'm going to come back to that in a bit. The SRT varies over more than a 10-fold range. So there we go. We know what the answers should be. We're actually getting reasonably close answers. They're not so far off, but our confidence in those answers is not so good. The 95% confidence limits with a data acquisition strategy like that, and with an experimental setup like we have, acquiring data with that much noise, we have a very high degree of uncertainty in these parameters. Okay, and so that's, again, sort of the scientific moral of this story. Let's go back and just play around with this for maybe 5 more minutes and hopefully learn a few more things. Maybe a little bit about learning PRISM, but maybe a little bit more about data simulation and analysis and experimental design. Right? In the background here is experimental design. Why do we want to screw around with something like this? We want to screw around with it so we understand what the effects are of how we measure, how we configure the experiment, how we measure the data in terms of our ability to extract information from the data, which is one of the goals, of course, of designing and performing an experiment. So I'm going to modify this again. Actually, at the moment, I'm going to modify the simulated data. I can do that through here. I can say change. I'm going to now change the simulated data. And so what am I going to do? I'm actually going to change the equation. I'm going to modify this equation so that I'm going to say y bar, instead of it being fractional saturation, I'm going to make it something that's a more realistic signal. So what I'm going to do is I'm going to put in a baseline signal. Right, so this is just sort of some what would be called DC offset in the experimental measurements. This is just some constant value that's sort of on your detector in the background. And I'm going to then say that let me go delta. So one of the slides in the PowerPoint covers this. I'm going to say my observed experimental observation, which in this case is that I'm simulating, given by y, the y variable, is going to be some constant value plus some scalar constant times the fractional saturation. So what this is saying, I'm getting a signal that is linearly proportional to fractional saturation, and then that includes some baseline value. So most detectors and most real experiments work this way. And so now, rather than simulating fractional saturation, which is theoretically very interesting and useful, but usually not what you're measuring in an experiment, I'm now simulating something that is much closer to actual experimental data. So now I need to go back to the rules for initial values. So I added 2 parameters, baseline and delta, and I'm now going to put in, whatever. These are arbitrary, but I'm going to say, what the hell? I'm going to say the baseline is 10 and the delta value is 100. And that means with no fractional saturation, this receptor, whatever measurement device I'm using, gives me a reading of 10. With full fractional saturation, it gives me a reading of 100. But this is in the absence of noise, and one of the things we're going to do now is see what effect noise has. Default constraints, we don't want to constrain these either, for the moment at least. And that's all we do for now. So, okay, so I've changed the equation. And the x values, I'm not going to change the x values or the parameter values. Well, I do need to set the parameter values for baseline. I don't know why it does not take the, well, this is a simulation. It does not take the initial values for simulation. So we have to input this value. But I'm going to use the same, I'm going to do the simulation with the values I just input as defaults. And we're going to leave the error the same, except for one thing. Now we're saying the data is going to go from basically 10 to 100. So 10% absolute noise at the maximum value of 100 is going to be about 10, or actually 11. So when the scale was 0 to 1, 10% noise at the highest values was 0.1. If the scale is 100, 10% noise at the top value, well, actually the top value will be 100 plus 10, so it'll be 110% is going to be about 11. So that is the same sort of magnitude of noise, but now on the new scale we've set, which is the scale of more realistic for what we get in an actual experiment. Okay, so we're good, and now we're going to, again, redo the simulation. And so it's the same, the data looks the same. The reason for that, although we're simulating noise, the computer does that with an algorithm to simulate noise. It is something called a pseudo-random number generator. The bottom line, if you ask the computer to simulate noise 2 times in a row, it will, depending, you can manipulate your program to do something different. But in general, because these random numbers are generated, it's a computer, it has to do defined calculations. There's a whole field of study sort of about random number generation in computer science. The bottom line is this is a random distribution of noise, but it's a computer. It's going to give you the same random distribution of noise every time. Well, it'll give you the same random simulation noise the first time you simulate it. This program is smart enough that if you do more than one simulation, it will actually give you different noise every time. But this looks very similar to the last go round because, in fact, the first time it does it, it uses the same noise. Well, it uses the same progression of random numbers, and that ends up giving you the same noise. So again, these are randomly distributed compared to the true data points. They just look like what you had before. So you basically have the same random distribution of noise, which is fine. And so that's going to be interesting then, because we have the same kind of, basically in effect the same noise, but we've now, rather than being on the Y bar scale, we're on a different scale. We're on an arbitrary scale. So actually we should change that. This is just some arbitrary, so what is this? This is an arbitrary concentration, well, arbitrary signal, proportional to, we can say proportional to Y bar, that's fine. Well, that's sort of a mouthful for an axis label, but anyway, that's what it is. All right, so now what I'm going to do? Well, now I'm going to curve fit it. And so think ahead. What's going to happen? Am I going to get back exactly the same parameter estimates, or won't I? Note that I have introduced 2 additional variables here. And what I'm now going to ask the program to do is not just estimate, as you'll see in a moment, I'm not going to ask the program just to estimate the most probable values of KD and SRT. I'm going to ask it to analyze, to get those probable values of those, and B and delta. So there are 2 more degrees of freedom here. And the reason for that is I don't know exactly what the baseline value is because it has noise. I don't know exactly what the saturating value is because it has noise. And so the best way to, the best thing I can do statistically is to use the mathematical apparatus that I have in place, the curve fitting methods, to get the best, most probable estimates of those. So let's go. Let's do it. So now I'm going to analyze it. well, we did an analysis before, yeah, the nonlinear fit. So we're gonna now change the nonlinear fit. All we're gonna do is we're gonna change it to the new binding equation, right? But this has been, oh, it didn't update this. What is that? Yeah, this is the right one. I think this is the new one. Yeah, this is the new one. So we're gonna just it actually kept a copy of the old one and renamed it with this appendix of 2. But this is the new one I just entered, so I'm going to fit it with that. And what do you get? We get a we get a good decent fit to the data, and let's see what parameters you've gotten out of this. And so we should go to results. And what do we get here? Okay, so let's look at the values that we get here out of this analysis. Wow, look at what's happened. The KD value, we know it should be 2. Instead, it's 5.7. Before we were within 10%, now we're way the hell off. The standard, it's telling us the KD is 5.8 plus or minus 5.9. So we don't know that KD very well. It's telling us SRT is less than is -5. That's physically impossible. It's giving us a baseline value of -13. We know that that's wrong. It's giving us a delta of 140. This is all way the hell off, and yet this is what an unbiased analysis of data with that of an experiment designed in that way and executed and acquired with that level of noise has given us. And so this is like a big take-home message. You have data that has noise in it, and this is actually an imperfectly designed experiment. I'm not going to go into that now, but you have an imperfectly designed experiment with it contains noise, and your parameter estimates are in some ways pretty far off. The 95% confidence limits on the KD are -7. 6.7 to 18, right? So this is an enormous range, right? Because think about it, a really, really low KD would be like, 0.0001. That would be 4 orders of magnitude below the actual KD. This is just a crazy range. We barely know anything about the KD. So, and what did we do compared to the last analysis? Well, we put in 2 more adjustable parameters because we needed them to match the data. When we need to determine that much more information from the experiment, our ability to infer anything from it reliably has just gone to hell. So to finish up here, I'm just going to do one more thing. I'm going to modify this one more time. I'm going to redo, actually, sorry, the wrong thing. I'm going to change the simulation to begin with, and I'm just going to remove the noise. And when I do that, what happens? Well, I get a nice curve. PRISM will automatically update all linked tables and analyses. So it automatically redid the curve fitting when I changed when I changed the simulation parameters and had new simulated data, it automatically redid the curve fitting for it. Looks like a perfect match. Let's go back and see what parameters it came up with. KD is 2.0 and SRT is 4. And basically, it has been unable to estimate the standard error for this because the match is so perfect. That's sort of a little mathematical glitch in a sense. So anyway, so you can, with perfect data, we can get perfect parameter values. But with even just 10% noise in the data, we got really rotten parameter values. So hopefully this screencast teaches you, some more of the, things. And I think this covers actually everything in PRISM you need to know to get through the class. And hopefully it begins to help you think in a more sophisticated way about experimental design, which is certainly one of the goals of the course. Bye.